When I say black hole, I am not talking about a cosmic vacuum cleaner. I am talking about a region of spacetime where gravity has pushed matter and light into a trap. The key idea is not the darkness. The key idea is curvature. In general relativity, mass and energy curve spacetime, and curved spacetime tells matter how to move. A black hole is what happens when that curvature becomes so steep that every future path points inward. The boundary of that trap is called the event horizon. It is not a solid surface. It is a location in spacetime. If you cross it, all possible routes that still move forward in time lead deeper in. Even a beam of light fired outward cannot escape, because outward no longer points to the outside in the way it does in flat space. That sounds abstract, so I use a thought experiment. Imagine standing on a hillside that gets steeper and steeper. At some point, the slope becomes a cliff. Past that edge, there is no path that goes up and away without first going down. The event horizon is not a cliff in space. It is a cliff in the structure of space-time itself. How do we know black holes are real if they do not emit light? We infer them from gravity. We watch stars orbit invisible masses. We see hot gas spiraling in and heating up, emitting X-rays before it vanishes. We detect gravitational waves from black holes merging, ripples in space-time itself. Each of these is a different line of evidence, and they agree on the same picture. Compact objects with enormous mass packed into a tiny volume, consistent with the equations of general relativity. Now I want to focus on formation. Nature makes black holes in more than one way, but the cleanest path starts with massive stars. A star is a balance between gravity pulling inward and pressure pushing outward. For most of a star's life, that outward pressure comes from nuclear fusion. Fusion releases energy. Energy supports the star, and the star resists collapse. The moment fusion can no longer provide enough pressure, gravity wins. In a very massive star, the core eventually builds up iron. Iron is a dead end for fusion because fusing iron does not release energy. When the core becomes iron-rich and massive enough, it collapses in a fraction of a second. Electrons and protons are crushed into neutrons, neutrinos flood out, and the outer layers can rebound in a supernova explosion. What remains depends on the mass of the core. If it is light enough, neutron pressure and nuclear forces can halt collapse, leaving a neutron star. If it is heavy enough, no known pressure can stop it. The collapse continues, an event horizon forms, and a stellar mass black hole is born. There is a common misunderstanding here. People imagine the star compressing into a point, then the horizon appears. In relativity, the horizon forms during collapse, before any central singularity becomes relevant. The horizon is a global feature of spacetime, and it can appear while matter is still falling inward. The singularity is what the math predicts at the center, but it is also where our current theory signals its own breakdown. General relativity does not include quantum physics, and at extreme densities, quantum effects should matter. So I treat the singularity as an unknown. The horizon is the part we can test. Stellar mass black holes are only one population. In the centers of galaxies, we find supermassive black holes, millions to billions of times the mass of the Sun. Their existence is supported by precise measurements. In our own galaxy, we track the orbits of stars near the radio source, called Sagittarius A star. Those stars move fast on tight orbits, around an invisible mass about 4 million solar masses, confined to a region smaller than our solar system. That is hard to explain with anything other than a black hole. How do supermassive black holes form? This is one of the active questions in astrophysics. We know they exist early in cosmic history. We see quasars when the universe was less than 1 billion years old, powered by black holes already 1 billion solar masses. Growing that big from a small stellar mass seed is challenging, because there are limits on how fast a black hole can accrete gas before radiation pressure pushes the gas away. That limit is called the Eddington limit. If you feed a black hole too aggressively, The disk shines so intensely that it fights its own fuel supply. So we consider other pathways. One idea is direct collapse. In the early universe, some pristine gas clouds may have avoided fragmenting into many stars. If cooling was suppressed, the cloud could collapse as a whole and form a massive black hole seed, perhaps 10,000 to 1,000,000 solar masses. Another idea is runaway growth in dense star clusters, where repeated mergers of massive stars and black holes build a larger seed. The evidence is still incomplete. We are trying to connect models to observations, using the demographics of black holes, the properties of early galaxies, and now gravitational wave detections that reveal black hole masses across cosmic time. To understand why black holes are common, I zoom out to large-scale structure. The universe began hot and nearly uniform, with tiny density fluctuations. We see those fluctuations imprinted in the cosmic microwave background. Over billions of years, gravity amplified them. Regions slightly denser than average pulled in more matter and grew into the cosmic web of filaments and clusters. This growth depends strongly on dark matter. Dark matter does not emit or absorb light, but it has gravity. We infer it from galaxy rotation curves, from gravitational lensing, from the hot gas in clusters, and from the pattern of fluctuations in the microwave background. In the early universe, ordinary matter was coupled to radiation, and pressure resisted collapse. Dark matter was not. It began clumping earlier, forming gravitational wells. After atoms formed and the universe became transparent, ordinary gas could fall into those wells, cool, form stars, and build galaxies. Black holes formed inside this structure because the deepest wells make the densest environments, and dense environments make massive stars, star clusters, and rapid accretion possible. So black hole formation is not isolated. It is linked to the scaffolding built by dark matter. Even supermassive black holes appear to co-evolve with their host galaxies. We see correlations between black hole mass and properties of the galactic bulge. That suggests feedback. When gas falls into a central black hole, some of the energy comes back out through radiation and jets. That energy can heat or expel gas, regulating star formation. We observe jets in radio galaxies, cavities carved in hot cluster gas, and winds from quasars. The details are complex, but the basic idea is testable. Black holes can influence galaxies, and galaxies feed black holes. Now I connect this to cosmic expansion and dark energy. The universe is expanding, and on the largest scales the expansion is accelerating. We call the driver dark energy. The simplest model is a cosmological constant, a constant energy density of space. We infer it from supernova distances, from the cosmic microwave background, and from large-scale structure. Dark energy does not matter much inside a galaxy. Gravity dominates there, and bound structures do not expand with the universe. That is why black holes can form and merge even in an accelerating universe. But dark energy matters for the long-term growth of structure. As acceleration continues, distant regions recede faster and faster, and the formation of new large structures slows down. In the far future, galaxies outside our local group will slip beyond our horizon, not a black hole horizon, but a cosmic event horizon set by expansion. This has consequences for black holes over cosmic time. The era of peak star formation is already in the past. Gas supplies decline, galaxies mature, and mergers become less frequent. Black holes will still merge, but the rate will drop. The biggest black holes will mostly grow by consuming stars and gas in their own galaxies, and by occasional mergers when galaxies collide. Dark energy gently pushes the universe toward isolation on large scales, while gravity keeps local islands bound. One of the most direct ways we test black hole physics is through gravitational waves. When two black holes orbit each other, they lose energy by radiating ripples in spacetime. The orbit shrinks, the frequency rises, and then they merge. Detectors like LIGO and Virgo have measured these signals. The waveforms match general relativity with impressive precision. From the signal, we infer the masses and spins of the black holes and the distance to the event. This is not a picture. It is a measurement of space-time dynamics. It also teaches us about formation channels. Different environments produce different mass distributions and spin alignments. We are building a population map, event by event. Another test comes from imaging the region around a supermassive black hole. The Event Horizon Telescope produced images of the shadow of the black hole in the galaxy M87, and later of Sagittarius A star. The shadow is not the horizon itself. It is a lensed silhouette created by light bending in the strong gravity near the horizon. The size of that shadow matches the predictions of general relativity for the measured mass. These observations do not prove every detail, but they strongly support the existence of horizons and the overall relativistic picture. Now I need to be honest about what remains unknown. The first unknown is the interior. What is the true nature of the central singularity? Does quantum gravity replace it with something finite? Does information that falls in get preserved in some subtle way? These questions connect to the black hole information problem and to the thermodynamics of horizons. We have strong theoretical clues, like Hawking radiation and black hole entropy, but we do not yet have direct experimental access to these quantum effects. The second unknown is the origin of the earliest supermassive black holes. We have plausible models, but we are still testing them. New data from the James Webb Space Telescope is finding very early galaxies and active black holes, and that is sharpening the puzzle.